Hello, welcome. In this short video, I'll give a brief introduction to the set theory. A set is basically defined as a collection of objects. These objects can be anything from numbers, fruits, furniture, etc. A good example of set is the set of natural numbers 1, 2, 3 and so on. N is the most commonly used symbol for set of natural numbers. And also we can have a set of fruits. Basically F consists of fruits such as apples, oranges, grapes, etc. So F is a set of fruits. Now there are multiple ways of representing any set. So for example, let us define a set A that consists of all the even numbers, that is set of all even numbers. This can also be represented as set of the numbers 2, 4, 6, 8 and so on. So this is basically set of all even numbers. And it can also be represented as follows, that is by using a mathematical expression such as 2x, where x is basically the set of natural numbers. Some of the interesting basics of set theory are: 1. A null set. This is commonly represented by the symbol phi. And this set basically consists of nothing. It is also known as empty set. The concept of subset, which is represented as A is a subset of B. This symbol represents the concept of subset. By using the representation, we can show it as B consists of many elements and also consists of the elements of A. So here A is completely contained in B. Graphically, this can be represented as, assuming this is the set B and this is set A. You see, the set A is completely inside the set B. So therefore A is a subset of B. And conversely, we have the concept of superset. That is, B is a superset of A. This symbol is used for the concept superset. A very good example for subset and is as follows. Consider the set of integers which has all the numbers from minus infinity to 0 and from 1 to plus infinity. So this is the set of integers, that is both positive integers and negative integers. And we have the set of numbers, that is set of natural numbers 1, 2, 3 and so on. Clearly the set of natural numbers is a subset of Z, that is the set of integers, since all the natural numbers are contained within the set Z. So the set N is a subset of Z. And conversely, set Z is a superset of the natural numbers N. The next operation is union of sets, which is usually represented as A union B. The symbol, which looks like a U, represents the union. Using a Venn diagram, that is the graphical representation of sets, we can illustrate the idea of union as follows. Consider a set A, set B, this is set B and this is set A. Now the total region outlined by this orange line is the set A union B. So basically the operation union combines the two sets. So a good example for union of sets is the combination or union of the set of whole numbers with the set of negative integers, which is represented by z minus, which consists of basically the numbers from minus infinity to minus 1. So the set of integers is basically the union of set of whole numbers with the set of negative integers. You see, if you combine all these numbers from the set of negative integers and also from the set of whole numbers, you get the set of integers. The next operation in set theory is intersection operator. Intersection. Which is usually represented as A intersection B. This is not an, this is the intersection operator. So using the Venn diagrams, we can represent as, so consider a set A and a set B, and then yellow area represents the set A intersection B. The operator intersection basically finds the common elements between the set A and B. So in terms of a good example, let us define a set A which consists of all the even numbers. That is, A is the set of all even numbers where x equals 1, 2, 3. And B is the set of multiples of 3. That is 3, 6, 9, 12 and so on. That is, B is set of multiples of 3 where x equals 1, 2, 3 and so on. So the set A intersection B consists of the common elements between A and B, that is 6, 12, 18 and so on. If you notice the elements in A intersection B, they are basically multiples of 6. So in this case, the intersection of the even numbers and the multiples of 3 is the set of multiples of 6. The next operation is the complement, which is denoted by the symbol C. You see, where A is a set. Graphically, this can be represented as follows. Consider a set. Consider a universal set U and another subset of this one, which is A. This is A. Then everything that is in the universal set but not in A is the A complement. So everything that is determined by. So in a complement set, the elements that are in basically the complement set AC is denoted by the following hatching sign. Mathematically, the complement operation can be represented as x that belongs to A is only true when x does not belong to A. Complement. Here is a good example for the complement operation. Consider the set of integers z. -3, -2, -1, 0, 1, 2, 3. So consider this is the universal set of integers. Then consider the set of whole numbers 0, 1, 2 and so on. Then the complement of this set of whole numbers is the set of negative integers, which is equal to minus infinity to minus 3, minus 2, minus 1. Therefore, the set of negative integers is the complement set of whole numbers, and the universal set is the set of integers. The next operation is the difference operation. Consider the universal set, and then we have set B, and we have set A. So the difference between A and B is denoted by the following region. A minus B is marked by this shade, and the value A minus B, or the set A and A difference B, can be also be written as A difference A intersection B. That is, all the elements of A that are not in the intersection A and B belong to the difference A and A minus B. And this can also be written as A intersection B complement. That is, common element between A and the elements of B complement. This set constitutes the difference set. A good example is the difference between the set of integers and the whole numbers, which is the set of negative integers. And similarly, the difference between the integers and the set of negative integers will give the set of whole numbers. And the difference between whole numbers and natural numbers is the set 0. And finally, the difference between the natural numbers in itself is the set of nothing, that is the empty set, the null set. The next property of sets is the disjoint sets. Two sets A and B are said to be disjoint if A intersection B is an empty set. Graphically, this is A and this is B, then obviously A intersection B is nothing, that is empty set, because there is nothing common between these two regions. A good example is the set of negative integers and the set of natural numbers, and the intersection between set of negative integers and natural numbers is nothing, that is an empty set. The intersection between the negative integers and the whole numbers is also an empty set. The next laws we discuss are known as De Morgan's laws. The first one is the complement of the set A union B is equal to A complement intersection B complement. And by the way, this law is called De Morgan's law. Okay, let's look at the proof using Venn diagram. Consider the universal set This is set A and this is set B. So if you notice here, A union B is given by this region. And by taking complement on this set, we get the set A union B complement. That is the following region. Hence, A union B is given by the region with this shade. Now, the other side of De Morgan's law, that is A complement intersection B complement, can be determined as follows. For example, the region A complement can be traced or shaded as follows. The region A complement can be shaded as follows. Notice that the set A complement also includes a part of the set B. We shade the area of B complement. That is shading in a different direction. This is B complement. So if you look carefully, the set A complement intersection B complement is given by the region that has the following pattern. So if you compare these two Venn diagrams, we can easily see that the complement of A union B is equal to A complement intersection B complement. This relation can also be derived mathematically as follows. A, consider the set on left hand side, that is A union B complement. So consider any element that belongs to this set A union B whole complement. Then this means that X does not belong to either A or X cannot belong to B because it belongs to A union B whole complement. This actually means that X belongs to A complement and also it belongs to B complement. So the first De Morgan's law is proved. A union B whole complement is equal to A complement intersection B complement. Similarly, the second law is A intersection B whole complement is equal to A complement in union B complement. This law can also be proved along the same lines. Thanks for